So in this video, we're going to talk about continuity. So back in an algebra class or a pre-cal class that you had, we defined a continuous function as something that doesn't have any breaks, doesn't have any holes, or you can draw it without ever picking your pencil up. So now we're going to look at a more formal definition, and that definition is actually built on the idea of limits. For a function to be continuous, three things has to happen at the point that we're questioning continuity. So we're calling that point x equals c. First off, the limit as x approaches c of f of x has to exist. Now, there's an underlying premise with this. Remember, for that limit to exist, the left hand and the right hand limits have to match up. So that's understood in that part of the definition. The left hand and the right hand limits have to match up, which is why the limit at c exists. Also, f of c has to exist. And then lastly, the limit as x approaches c of f of x has to equal f of c. If all three of those things happen, then we have a continuous function. So now when we talk about why is it continuous, because remember, calculus really answers a lot of the questions as to why this happens, we can use one of those three reasons for a function that's not continuous. And if a function is continuous, we can show all three of those exist at whatever point we have in question. So usually we talk about where functions have problems, especially when we have a graph like this. So here they're asking us to use the definition of continuity to discuss the continuity of the function whose graph is shown below. So this is a piecewise function. Now you can see there's definitely some places that are interesting here. This is going to be an interesting place, and that's happening at x equals -3. This is going to be an interesting place because of that gap. So we're going to look at what happens at -1. And this is going to be interesting here because we have a hole, but we have a point filled in. So that's happening at x equals 2. And then at x equals 4, we have something interesting happening also. Now, everywhere else, this function is going to be continuous. If we were to test what's going on at -5, all the criteria would be fine. We're really just concerned with those interesting places. So let's look at this definition of continuity here. If we look at -3, x equals -3. To test the definition of continuity, we first have to look at the limit as x approaches -3. So there's our first piece. So does the limit exist at -3 for this function? And the answer is yes. That limit ends up being 3. The left hand limit's 3, the right hand limit's 3, so the limit at -3 is defined to be 3. Second question we have to answer is, does f of -3 exist? And in this case, no, f of -3 does not exist, which means this function is not continuous. So if you were asked, why is this function not continuous at -3, this is why. Because that definition of continuity falls apart when we reach that second part, which is defining what f of c is. So now let's examine what's going on at -1. So at -1, visually we can see there's a gap here. So let's start by looking at the limit. We take the limit as x approaches -1 of f of x. So if you look at this, that left-hand limit is 1, and that right-hand limit is 2. So this limit does not exist because the left and the right-hand limits don't match up. So our limit doesn't exist. So this function is not continuous at x equals -1, because the first part of that definition actually fell apart on us. That limit doesn't exist. So there's no reason for us to go further in the definition if the first part doesn't work. Or, like in the last example, if the second part doesn't work. We know it's not continuous, and now we know the why. The why for this one is that the limit doesn't exist. So now let's look at 2. When we look at x equals 2, we'll notice we see a gap here. So let's figure out what's happening in terms of that definition of continuity. We're going to take the limit as x approaches 2. And you can see the left and the right hand limits are going to match up. And we're going to get 5 for that limit. So the first part of the definition is fine. The second part of the definition is looking at, does f of 2 exist? And the answer is yes. F of 2 exists. And in fact, f of 2 in this case is equal to 3. So the first two pieces of the definition are fine. Now let's look at the third one. Does the limit as x approaches c of f of x equal f of c? And if we look at this, the answer is no, they don't equal each other. The limit as we approach 2 of f of x was equal to 5. And that's not equal to what our f of 2 was, which was 3. So the reason this one is not continuous is because the limit did not equal what the value of the function was at that point. And then let's look at 4. So if we look at 4, we're looking at visually, we have a gap. So let's test our definition here. Which piece of the definition falls apart? If I take the limit as x approaches 4, notice that that limit's not defined. So right off the bat in this problem, we have a big problem because that limit doesn't exist. The left-hand limit, if we were to look at it, is equal to 4, but that right-hand limit is equal to 2. So we would say this is not continuous, and the reason that it's not continuous is because that limit right off the bat doesn't exist. Now, the second part of the definition would kind of fall apart here too. F of 4 doesn't exist for this problem either because we have open circles at both of those pieces of that piecewise function. So there's two reasons why this doesn't exist. Either reason is enough to say this function is not going to be continuous. So now let's go back and look at, what if we looked at negative x equals -5 here? Can we show that it would be continuous at x equals -5? So I'm going to go up here and write this. So first off, the limit has to exist. And we can see that that limit, as we come in from the left and from the right, does exist, and it's equal to 5. And then f of -5 has to exist. So what is the value of the function at -5? Well, it's equal to 5. And then, does the limit at -5 equal the value of the function at -5? And yes, they do each equal to each other because we got 5 for both of those. So we can conclude that this is continuous at x equals -5. So we've got 4 places where we have discontinuities, and now we can see why exactly it's discontinuous based on that definition of continuity. And we can also show that something's continuous on a function everywhere. So what if we were to look at an equation? Could we figure out continuity based on that? Well, we could always graph the equation, and sometimes that's useful to do that. Or we could think about what the equation looks like. So let's look at A. To test the definition of continuity, we have to look at three things. The limit, in this case, as x approaches 1, of the function x plus 1. So if we were to evaluate that limit, we're going to get 2. Then we have to look at f of 1. F of 1 is equal to 2. And 3 is asking, is the limit as x approaches 1 of the function equal to the function evaluated? And in this case, it is. So we would say this is continuous at x equals 1. I'm going to say therefore, so those 3 dots means therefore. Now, that makes sense because this is the equation of a line. It has a y-intercept of 1 and a slope of 1. And we know lines are continuous everywhere. So we're not going to have any problems with continuity here. But let's look at B. In part B, we're looking at a rational function, x squared minus 1 over x minus 1. Now notice that function is going to reduce. We could factor the top. And then we can reduce this. So this is going to look like the line x plus 1 as long as x is not equal to 1. And notice that's where they're asking us about this function and what's going on there. So this function, if we were to graph it, has a y-intercept of 1, and then we're going to move up 1 over 1. So it would look like this, but there's going to be a hole at x equals 1. So instead of a solid dot here, we actually need an open circle there to show that hole. So now let's go through that limit definition. First thing we have to test is, does the limit exist? Well, to take that limit, we have to look at that reduced form. And that limit is going to exist, and it's going to be equal to 2. We could also see that with the graph. If I come in from the left and come in from the right, I'm approaching 2 from both sides. Now we need to ask, does f of 1 exist? Or g of 1, rather. They're calling this function g. Well, in this case, g of 1 does not exist because that's actually an issue in the domain. So we know that g of 1 doesn't exist. That second piece of that definition of continuity falls apart. So we can say, therefore, this function is not continuous at x equals 1. And the reason it's not is because g of 1 does not exist for this particular function.